Well, what I know is that I attempted to call their attention after the report came out. I looked at it and, it had a physical form, but it also lives online. You can search for it. I could see that T-layer weren't mentioned, mice weren't mentioned, rodents aren't mentioned. So, I tried to alert them to the fact that they had screwed up. Joe Rogan has done it again. He recently revealed a shocker that has been making waves on his famous podcast, The Joe Rogan Experience. Scientists have released something into the United States without the public's knowledge. From secret experiments to unintended side effects, we will be unraveling the truth behind this jaw-dropping revelation. You won't want to miss this. Lyme disease. Imagine enjoying a beautiful day outdoors only to later discover a tiny, unwelcome hitchhiker. A tick. But not just any tick, as you'll soon come to see. This small creature can carry a big problem, Lyme disease. Lyme disease is a serious illness caused by bacteria transmitted through the bite of an infected blackleg tick, commonly known as a deer tick. These ticks are prevalent in wooded and grassy areas. So, how do they get infected? These ticks often feed on a species of mice. Which species is this? These mice are key carriers of the bacteria we will discuss more soon in this video. The impact of Lyme disease on public health is significant and has been a cause for concern for the Centers for Disease Control and Prevention, CDC. In the United States alone, the number of reported cases has been steadily increasing. According to the CDC, over 63,000 cases of Lyme disease were reported in 2022. However, recent estimates suggest that approximately 406,000 people have been diagnosed and treated for Lyme disease each year in the United States. Then it gets scarier. In some circumstances, Lyme disease can be fatal. Between 1985 and 2019, there have been 11 reported fatalities worldwide due to Lyme carditis, a heart condition linked to Lyme disease. This shows that Lyme disease can be fatal, and there is a possibility that the number of fatalities could be more than reported, which is a major problem. Underreporting complicates efforts to understand the true prevalence of the disease and disrupts public health initiatives aimed at controlling its spread. Even when reported, misdiagnosis has occurred, often due to a lack of awareness among healthcare providers and the public. To grasp the size of the Lyme disease problem and gather good information on rapid diagnostics and treatment, it's crucial to overcome misdiagnosis. This happens because the symptoms of Lyme disease, which can be debilitating and vary among individuals, easily mimic those of other illnesses. Early signs often include fever, headache, fatigue, and a characteristic skin rash called erythema migrans, or the bull's-eyed rash. If left untreated, the infection can spread to joints, the heart, and the nervous system, leading to more severe complications such as arthritis, heart palpitations, neurological issues, and in the worst case, loss of life. The chronic nature of these symptoms can significantly impact a person's quality of life, making early detection and treatment crucial. The disease not only affects the quality of life of those infected but also places a substantial burden on the healthcare system. The costs associated with diagnosis, treatment, and long-term care for Lyme disease patients are considerable. As more people are diagnosed, the demand for medical resources and public health interventions grows, skyrocketing. All of these problems are caused by mice, ticks, and bacteria. The origin of Lyme disease lies with the white-footed mouse, Paramyscus leucopus, a small, seemingly harmless rodent with distinctive white feet and large eyes. They are cute forest dwellers, but they are also the primary carriers of the bacterium Borrelia burgdorferi. When deer ticks feed on the mice, they pick up the bacteria which they end up transmitting to humans and other animals. So, the mice are a critical link in the chain of Lyme disease transmission. The impact of these tiny mice is profound. In areas where these mice are abundant, the incidence of Lyme disease is significantly higher. This is why Lyme disease cases have been on the rise in regions like the northeastern United States. Eliminating the mice is key, but it's not so easy to achieve. If it were, their population would have significantly reduced since Lyme disease has been a recognized health issue in the United States since the 1970s. The disease was first identified in Lyme, Connecticut in 1975, when a group of children and adults began experiencing strange symptoms like swollen knees, paralysis, skin rashes, headaches, and severe chronic fatigue. The renowned Dr. Alan Steer and his colleagues then described this new phenomenon as Lyme disease after investigating these symptoms. The doctor and his team conducted extensive investigations and identified a pattern linking these symptoms to tick bites. Lyme disease patients suffer from long-term symptoms, and it all has to do with an immune system marker found in the blood. This groundbreaking work culminated in the identification of Borrelia burgdorferi as the causative agent of Lyme disease. The bacterium was officially classified in 1981. However, The discovery of the disease in the 1970s and the identification of the bacteria in the 1980s are relatively new discoveries. Interestingly, research has shown that the Lyme disease bacterium has been present in North America for thousands of years. The disease's prevalence only increased significantly due to ecological changes, such as forest fragmentation and the population explosion of deer ticks, which created optimal conditions for ticks to thrive. The emergence of Lyme disease as a significant health issue in the 1970s marked a turning point in our understanding of tick-borne illnesses. Before its identification, the symptoms experienced by those infected were often misdiagnosed or attributed to other conditions. Since that time, thousands of new infections have been reported in the United States alone. The discovery of Borrelia burgdorferi provided a crucial breakthrough, allowing for more accurate diagnosis and treatment. After this breakthrough, scientists addressed the challenge of Lyme disease with a broader approach. At first, public health initiatives focused on raising awareness about the disease, promoting preventive measures, and ensuring access to accurate diagnosis and effective treatment. Additionally, scientists implemented ecological management strategies essential to reducing the risk of tick-borne diseases. However, as robust as it appeared, their efforts were not enough. They needed something more to tackle this ecological problem. So, they added more efforts towards studying, understanding, and getting the correct diagnosis to fight against Lyme disease. This approach yielded yet another breakthrough as scientists developed different diagnostic tests, such as the enzyme-linked immunosorbent assay, ELISA, and Western blot. Initially, the primary method to combat Lyme disease was the use of antibiotic treatments like doxycycline, cefuroxime, and amoxicillin. These antibiotics are typically administered for 2 to 4 weeks, depending on the severity of the infection. The key to the quick effectiveness of the antibiotics was early treatment, as it can then easily prevent the progression of the disease and the development of more severe symptoms. Despite the effectiveness of antibiotics in treating early-stage Lyme disease, some patients continue to experience symptoms even after completing their treatment. This condition is known as post-treatment Lyme disease syndrome, PTLDS, and it remains a topic of ongoing research and debate. PTLDS is characterized by persistent symptoms such as fatigue, muscle and joint pain, and cognitive difficulties. The exact cause of PTLDS is not well understood, and there is currently no consensus on the best approach to manage these persistent symptoms. So, it became important to increase publicity about this disease. The CDC launched awareness campaigns to educate the public about the disease, its symptoms, and preventive measures. These campaigns emphasized the importance of avoiding tick bites by using repellents, wearing protective clothing, and performing regular tick checks after spending time outdoors. If you're out for a walk in grassy or wilderness areas, make sure that you're wearing long sleeves, long pants, and socks with your shoes. Those initiatives by the CDC were necessary, but research continued, and in the late 1990s, a significant advancement was made. Finally, the first Lyme disease vaccine, Elway-Amerix, was developed by SmithKline Beecham, now GlaxoSmithKline. The vaccine worked by stimulating the immune system to produce antibodies that attack the Lyme bacteria in the tick's gut before it could enter the human body. Unfortunately, the vaccine was a short-lived victory. Due to low demand and concerns about side effects, the vaccine was withdrawn from the market in 2002. What was next to combat this relentless disease? It seemed that nothing significant was done. Had the scientists given up? Joe Rogan's podcast, The Joe Rogan Experience, has 14.5 million followers on Spotify as of late March 2024, and the number of listeners is likely to have increased since the podcast isn't exclusive. Rogan's podcasts cover different topics and host various guests, some of whom can be controversial. It was on his podcast that he discussed a controversial leak from an anonymous hacker about how scientists have been working to deal with the threat posed by Lyme disease. So, what did the hacker claim? Scientists at a prestigious research institute in Massachusetts have been tirelessly working to fight Lyme disease on a secret project named Mice Against Ticks. According to the hacker and the documents he released, the project involves the release of hundreds of thousands of genetically engineered white-footed mice into the public. Based on that reveal, have these scientists caused a mice invasion without formally announcing it to the public? Scary, right? But that's not all. Achievements in the laboratory were impressive, but the hacker also revealed that the main aim of the scientists was to study these rats in the real world as they had been bred in a laboratory. However, this experiment raises significant ethical and ecological concerns. Releasing genetically modified organisms into the wild without public knowledge or consent is controversial. But that's just one part. There are also potential environmental consequences to consider. Altering one species can have unforeseen ripple effects throughout the ecosystem, affecting other wildlife and plant species. But can the scientists be blamed for their current efforts? After all, this was not the first time. When genetically modified research has taken place, one of the most famous positive impacts of genetically modified research is tied to the development of artificial insulin to combat diabetes in the late 1970s. A challenge faced by scientists then was that traditionally, insulin was extracted from pigs and cows, but this method had limitations, including supply issues and allergic reactions in some patients. So, scientists tried another approach. This new approach yielded results when, in 1973, scientists Herbert Boyer and Stanley Cohen successfully transferred genes from one organism to another. They used a small circular piece of DNA to introduce a gene from another organism into Escherichia coli, *E. coli*, a common bacterium. Their work showed that it was possible to manipulate the genetic code of organisms, leading to advancements that would revolutionize various fields from agriculture to medicine. A few years later, in 1978, scientists achieved another monumental milestone by engineering E. coli to produce human insulin. This was a groundbreaking achievement, as it provided a reliable and safe source of insulin for people with diabetes. The genetically modified E. coli revolutionized diabetes treatment, making insulin more accessible and affordable for millions of people worldwide. This type of research has been successful, and in the past, specifically in the 1980s, scientists developed transgenic mice, which are genetically modified to carry genes from other species. In short, these mice became invaluable tools for studying different types of human diseases by mimicking conditions like Alzheimer's and cancer to have a better understanding and test new treatments. From the perspective of scientists, genetic engineering has yielded positive results, and they were hoping it would yield them again with their experimental laboratory white-footed mice on Nantucket Island. These mice were mainly designed to combat Lyme disease by reducing the population of ticks that spread the disease. In essence, they possess the ability or are capable of disrupting the life cycle of ticks, thereby reducing the incidence of the disease. So, how have these super mice performed? After a thorough look at the leaked documents, it was discovered that not only did they release the mice, but they did so in a multitude of numbers. They recorded a release of 100,000 genetically modified white-footed mice. According to confidential documents, the plan involved releasing these genetically modified mice in carefully timed batches. Every 2.5 months, new groups of 20,000 to 40,000 mice would be introduced into the environment over the course of a year. This staggered release was designed to ensure a steady integration of the disease-resistant genes into the wild mouse population. The goal was to create a robust population of mice that are immune to Lyme disease. As these genetically modified mice breed with the existing wild mice, their resistance to Borrelia burgdorferi would spread, reducing the number of bacteria-carrying mice and consequently the number of infected ticks. This approach is not just about numbers, it's about timing and precision. By releasing the mice in batches, scientists can monitor the impact and make adjustments as needed. This methodical rollout is crucial for the success of the project, ensuring that the genetically modified mice have the best chance to thrive and pass on their disease-resistant genes. This could lead to fewer cases of the disease in humans, alleviating the health burden and preventing the chronic symptoms that can arise from untreated infections. To progress with their experiment, the scientists released another batch on the island of Nantucket, a picturesque island off the coast of Massachusetts. Nantucket was chosen as the site for this experiment due to its high incidence of Lyme disease and its relatively contained ecosystem. The county has had over 500 confirmed Lyme disease cases since 2019. This number only includes confirmed laboratory tests and does not account for cases where clinicians diagnosed Lyme disease based on symptoms, such as the characteristic bullseye rash, and prescribed antibiotics without laboratory confirmation. While fatalities can be rare, the real challenge lies in the significant health burden and the risk of chronic symptoms if the disease isn't treated promptly. The island's isolated nature made it an ideal location for a controlled study, allowing scientists to monitor the effects of the genetically engineered mice without the complexities of a mainland environment. However, as much as speed is important, the effect of what the scientists have done will take years. Apart from the fact that breeding out the ability of the mice to host the Lyme disease-causing bacterium will take time, the effectiveness of the genetically modified mice in reducing Lyme disease cases will be assessed over time. The researchers need to monitor the ecological impact of the release of the mice. They will closely observe how the genetically modified mice interact with their environment and other species. This includes tracking any unintended consequences, such as changes in the behavior of local predators or shifts in the ecosystem balance. The goal is to ensure that the introduction of these mice does not disrupt the natural order in unforeseen ways. The scientists will then collect data on the number of infected ticks and new Lyme disease cases in humans. This data will help determine whether the strategy is working as intended and if any adjustments are needed. If successful, the experiment on Nantucket could pave the way for similar initiatives in other regions affected by Lyme disease. It could also set a precedent for the use of genetic engineering in combating other vector-borne diseases, such as malaria and the Zika virus. The implications of this experiment extend beyond public health, touching on broader questions about the role of genetic engineering in society and the ethical boundaries of scientific innovation. According to the document, the idea was originally inspired by a Massachusetts Institute of Technology professor who introduced the concept to the Nantucket Board of Health. The professor and the board presented the idea to about 24 residents, who expressed their support. Still, imagine unleashing tens of thousands of genetically engineered mice just because a few people think it's a good idea. Was that the correct thing to do? There have been arguments that those who agreed to the plan can't be blamed, as most were not fully educated on the advantages and disadvantages of the proposal. Moreover, the disease had caused so much harm that they were desperate for any solution that promised relief. Who could blame them? Although controversial, the potential impact of this strategy is enormous. By reducing the number of infected ticks, the overall risk of Lyme disease transmission to humans could be dramatically lowered. This approach not only targets the root of the problem but also offers a sustainable solution to a growing public health concern. This approach could revolutionize the way we tackle Lyme disease. It represents a shift from reactive treatments to proactive prevention, targeting the root of the problem rather than just the symptoms. The potential benefits are enormous, offering hope to regions plagued by this disease. The uncertain fight against Lyme disease, however, according to a guest on the Joe Rogan Experience, has hit a snag. While the idea of using genetically modified mice to combat Lyme disease is innovative and promising, it is not without its potential drawbacks. One of the primary concerns is the potential for ecological imbalance. The white-footed mouse plays a crucial role in its natural habitat, serving as both predator and prey. These mice, engineered to be disease-resistant, possess enhanced abilities that could disrupt existing food chains in unforeseen ways. By introducing genetically modified mice, scientists could inadvertently disrupt this delicate balance. One of the primary concerns is their extraordinary hunting potential. These genetically modified mice could become super predators, outcompeting their wild counterparts and leading to overhunting. This could quickly decimate the populations of their natural prey, causing a ripple effect throughout the ecosystem. When the prey species are driven to near extinction, the balance of the ecosystem is thrown into disarray. The consequences of such disruption are far-reaching. With their natural food sources depleted, these genetically modified mice may turn to alternative sources of sustenance. This could lead them to invade homes and public spaces in search of food, increasing the likelihood of human-mouse interactions. Such interactions are not only a nuisance but could also pose significant health risks, as mice are known carriers of various diseases. Predators that rely on these prey species for food might struggle to survive, leading to further declines in biodiversity. The loss of key species can alter the structure and function of the ecosystem, potentially leading to the collapse of certain ecological communities. In addition to these ecological concerns, there are ethical and social implications to consider. The idea of releasing genetically modified organisms into the wild is controversial, with public opinion often divided. Some people worry about the long-term effects and the potential for unforeseen consequences. Engaging with local communities and stakeholders is crucial to address these concerns and gain public support. Another significant risk is gene flow, where the modified genes spread beyond the target population. These genes could potentially transfer to other species. For example, if the disease-resistant genes were to spread to other rodent species, it could alter their interactions with the environment and other organisms. This could result in new ecological dynamics that are difficult to predict and manage. The introduction of genetically modified mice could also impact biodiversity. By altering the genetic makeup of a key species, we risk reducing genetic diversity within the population. This reduction in diversity can make the population more vulnerable to diseases and environmental changes, potentially leading to a decline in the overall health of the ecosystem. Effective regulation and governance are essential to ensure the safe release of genetically modified mice. Developing comprehensive guidelines and oversight mechanisms to monitor the impact of these organisms is crucial. However, creating and enforcing these regulations can be challenging, especially on a global scale. Come to think of it, the entire project is a grand speculation. The idea of using genetically modified mice to combat Lyme disease is as ambitious as it is uncertain. Scientists have forged ahead with their decision, driven by the hope of a breakthrough. Despite these potential setbacks, the researchers remain undeterred. They have decided to press on, believing that the potential benefits far outweigh the risks. The stakes are high, yet the scientists are not backing down. They meticulously monitor the released mice, gathering data and making adjustments as needed. Their determination is fueled by the urgent need to find a solution to Lyme disease, which continues to pose a significant health threat in many regions.